In this video, we will see about the ideal transformer under no load conditions. First, we will see the characteristics of an ideal transformer. Then we will draw the phasor diagram and derive the equation for EMF. And finally, we will see about the turns ratio for step up transformer and step down transformer. First, let us recall what do you mean by a transformer. So we know a transformer is a circuit which is used to transfer electrical energy from one circuit to another. So here you can see this is the magnetic core over which two windings will be wound. So the first winding is called the primary winding, to which we will connect the alternating AC supply, and the second winding is called the secondary winding, to which load will be connected. So we will be giving the electrical energy to one winding and we will be taking the output from the second winding. So that is why it is used to transfer electrical energy from one circuit to another. So transformer is a static piece, meaning that there are no moving parts in a transformer. So this is the magnetic core with primary and secondary windings. So we can give an alternating AC supply to the transformer. You should always remember you cannot give a direct current or DC voltage for a transformer. You have to give an alternating current for the transformer. So this is the sinusoidal voltage which is given as an input for the transformer primary winding. And you have to remember that there will be no change in frequency in a transformer. That is, if I give a 50 Hz AC supply, what I get here also in the output, I will get only 50 Hz. Okay, I cannot change the frequency of the AC supply here. But I can change the magnitude of the voltage. Suppose if I give here 220 volts, I can get 110 volts or 100 volt, whatever it is. I can also increase the voltage. So the output magnitude of the output voltage can be increased or decreased. The transformer works on the principle of electromagnetic induction, that is based on the Faraday's law. So according to Faraday's law, whenever there is a rate of change of flux, an EMF will be induced. So since we are giving electrical input, that is a AC sinusoidal voltage for the primary winding, the flux will also be sinusoidal. Due to the change in the flux, an EMF will be induced. So we will get an electrical output. So our input is electrical, output is also electrical. But if you see here, there is no physical connection between them. These two coils or these two circuits, that is the source and the load, are connected magnetically. So there is no physical connection, only magnetic coupling is there. So it will be like this. So there will be no physical connection here, but they will be magnetically coupled. Let's see about ideal transformer first. So the two main parts in any transformer is, one is the winding. So it includes both primary and secondary winding, and the other important part is the magnetic core. So we are going to make some assumptions so that the transformer remains ideal. Okay, practically we don't have any ideal transformer, but to analyze the practical transformer, we need to study the ideal transformer. So we are making some assumptions and we assume that the transformer is ideal, and we will derive some relations which will be helpful to analyze the practical transformer. So the first assumption is that there is no winding resistance. Okay, so this winding, primary and secondary winding, is not having any resistance. Normally, what is this winding? It is just a inductive coil. So the coil is purely inductive and there is no resistance in the coil. When there is no resistance in the coil, there will be no I square loss or copper loss. I square R loss will not be there in the windings. Okay. So the first assumption is there is no winding resistance. Second one is there is no leakage flux. So we will see what is this leakage flux. When you give the supply to the primary winding, current is flowing and it creates a flux. This flux will be linking with both primary and secondary. But apart from this flux, there will also be some flux which will be passing through the air, or this flux will not link with the secondary. So this flux is called the leakage flux. In practical transformer, leakage flux will be there, but we assume here that there is no leakage flux. The next assumption is there is no core loss. So we have seen the two major parts. One of the part is the winding, the other one is the magnetic core for a transformer. So this transformer core, or the properties of the magnetic properties of this transformer core, plays a major role in the performance of the transformer. So the magnetic core, two properties are important. One is the BH curve, another one is the relative permeability mu R of the material. What type of core we use, depending upon that, these things will change. So we will see about this one first. So core loss are of two types. One is hysteresis and another one is eddy current. So first, hysteresis loss, you see the BH curve. The whole area, the area under this curve represents the hysteresis loss. So if you have such a big area, it means that hysteresis loss is going to be very high. We always prefer to have a small one, or ideally it should be a linear one. A straight line should be there. The next one is eddy current loss. So in magnetic core, when current passes through it creates some eddy current will flow and it will create a loss. So you can see here, this current will be circulating here, which will create some losses. So normally to reduce the eddy current, we will have some type of laminations. That is, instead of a single piece, we will have a thin laminations to reduce the flow of eddy current. Okay, so we will see in detail about hysteresis loss and eddy current loss in when we study about the losses in a transformer. Okay, so now our assumption is that there is no core loss. It means that there is no hysteresis loss, no eddy current loss. Next one is the core has high permeability or constant permeability. So if you see the BH curve, you can see three different curves. It depends upon the type of material we use, the curve will differ. Now you can see here this one has lower permeability and this one has higher permeability. So how does this affect the performance of the transformer? So if you see here, what is the slope of this one? Actually, the slope of this one indicates the relative permeability, slope of this curve. So del B by del H. So what is this H? The magnetic field intensity H, that is equal to Ni by L. Let me write it here. So it is Ni, H is equal to Ni by L. This is L is the length of the magnetic path, N is the number of turns, and I is the current. So when H is small, it means that I is small. Suppose if I want to operate at this B, so I need this much current. So I need this much current. Whereas if I use this type of material, or if my BH curve is here, I need only this much current. So the magnetizing current required to magnetize the core will be less if this mu r is very high. Okay. So mu r should be very high. Ideally it should be infinite. Or we can say it should be along this B axis. So these are the four assumptions for an ideal transformer, or we can say these are the four characteristics of an ideal transformer. Now let us see about ideal transformer under no load conditions. So first I am taking the magnetic core. We will wind the primary winding. to which we have to give the sinusoidal AC supply voltage. So let us mark it as V1. So V1 is the voltage, sinusoidal voltage applied to the primary winding. Then we have secondary winding, which is left open because we are considering no load condition. So no load is connected here, it is left open. Primary winding has N1 number of turns and secondary winding has N2 number of turns. So when we give the voltage V1 to the primary winding, a small magnetizing current will flow in the windings. So this current is linking with all the number of turns in the primary winding, which will produce a magnetomotive force MMF. So MMF is equivalent to EMF in electric circuits. In electric circuits, EMF is a voltage which will drive the current in the circuit. In magnetic circuit, this MMF will drive the flux in the circuit. So here MMF is given by N into I. In this particular case, MMF will be equal to N1 because we have taken primary number of turns N1 into what is the current I mu. So this MMF will create a flux in this core, flux phi. Now you have to remember one thing. Already we have assumed that the winding does not have any resistance. It is purely inductance. So in a pure inductive circuit, the current lags the voltage by 90 degree. So you can see here, if I take I have taken V1 in this direction, the current I mu, magnetizing current, is flowing through a pure inductive coil. So the current lags V by 90 degree. But this I and this flux are directly proportional because MMF is N into I, as N is fixed quantity, I is directly proportional to flux. So both flux and current lags the voltage by 90 degree. Okay. Now according to Faraday's law, EMF will be induced in the circuit when there is a rate of change of flux. So Faraday's law is E is equal to minus N into d phi by dt, where this minus comes because of the Lenz's law. So according to Lenz's law, this EMF, developed EMF, will be opposing the cause producing it. So here we are giving a supply and it is producing a current I. So this EMF should be such that it should oppose the current producing it. So always a minus sign will be included due to this Lenz's law. Okay. Now here voltage is sinusoidal, flux is also sinusoidal. So due to this sinusoidal flux, an EMF is induced. There will be a rate of change of flux. So EMF will be induced. E1 will be there. So E1 will be always in antiphase with V1 because it should oppose the source producing it. Okay. So V1 and E1 are in antiphase. Now the voltage E1 is given by minus N1 into d phi by dt. So this small, normally in electrical circuits, small letters are used to denote the instantaneous value and capital letters are used to denote the RMS value. So the instantaneous EM of E1 is equal to minus N into d phi by dt. Similarly, this flux links with the secondary coil also, and due to the rate of change of flux, an EMF will be induced in the secondary coil, that is the E2. Since the secondary side is open, there will be no current here and V2 will be equal to E2. So if you can see E2 here. Since I have taken a step up transformer, see the number of coils in primary is less compared to number of coils in the number of turns in the secondary. So I have taken E2 greater than E1. If you have drawn only less number of turns here, you make your E2 somewhere here, okay, less than E1. Next, we will write the EMF equation of the transformer. So the induced EMF is given by rate of change of flux per turn. But our flux is a sinusoidal quantity. You see the total time period is T. So this will be half of that. So T by 2 and this will be T by 4. So the average rate of change of flux is equal to pi m, the maximum flux. What is the time period? T by 4. So I can write T by 4 or 1 by 4 F because F is equal to 1 by T. Okay, time period and frequency are inversely proportional. T is equal to 1 by F. So I am writing 1 by 4F, that is equal to 4F by M. Now the average induced EMF per turn is 4F by M. This flux is varying sinusoidally. So for a sinusoidal quantity, the RMS value can be found from the form factor. So the form factor is equal to RMS value by average value, which is equal to 1.11. It is a standard value for sinusoidal quantity. So if you have a sine waveform, your form factor is always 1.11. So the RMS value of a induced EMF is, you can find the RMS value from this one, 1.11 into average value. So average we have already derived it. So you will get 4.44 F by M. So the RMS value of the induced EMF in the primary winding. Here we have taken for one turn. You multiply with the number of turns in the primary winding N1. So 4.44 F by M into N1. So for secondary winding, we can write instead of N1, you just write N2. Okay. So you got two equations now. So E2 and E1. Let us divide these two. So if you divide these two, you will get, you can cancel the common terms. So it will become E2 by E1 equal to N2 by N1. It means that the turns, this is called actually called the turns ratio or transformation ratio or transformer ratio. So here different notations are used. Sometimes this small k can be used or a small n is used. A is also used. So the transformation ratio K is given by N2 by N1, which is nothing but it is equal to E2 by E1. Now let us see the turns ratio of a step down transformer. So if the number of turns in the primary is 10 and the number of turns in the secondary is 5, K will be the turns ratio is equal to N2 by N1, that is equal to 5 by 10. So the turns ratio is 0.5. Okay, so you have to remember that in a step down transformer, the secondary turns is less than the primary turns and K will be always less than 1. Okay. And what is the output voltage? So suppose if the input voltage is 200, what will be the output voltage for a step down transformer? So V2 is equal to, from this relation, we are getting V2 equal to K times V1. So 0.5 is the K we got. 0.5 into 200 will give you 100 volts. Okay. So the output voltage is less than the input voltage in a step down transformer. How to draw the step down transformer? You should always draw that number of turns is more in the primary compared to the secondary. Okay. For step up transformer, K is equal to, I have taken here N1 equal to 4 and N2 equal to 10. So K will be 10 by 4, that is equal to 2.5. So you can see that for a step up transformer, always this transformation ratio, turns ratio is greater than 1. And in case if the input voltage is 200 volt, V2 is equal to K times V1, which comes from this one. So K is 2.5 into 200. So you will get 500 volts. So in step up transformer, always the output voltage is greater than the input voltage and turns ratio will be greater than 1. And while drawing a step up transformer, always remember that the number of turns in the secondary should be greater than the primary. Let us summarize about the ideal transformer. We have assumed that there is no winding resistance, no leakage flux, no core loss. Core loss includes hysteresis and eddy current loss. and core has a constant high permeability. And the turns ratio of a transformer is given by N2 by N1. And for a step down transformer, the turns ratio is less than 1, whereas for a step up transformer, it is greater than 1. If you like the video, do subscribe to Read Electric Vehicle channel. Thank you.